Good afternoon and welcome everybody to the keynote speech of Riccardo De Gaudenzi. Okay? I am really happy that he accepted to come here. It was not trivial for him, I know, because he has a lot of work. Just as a short introduction, I'll tell you that he got his master's from the University of Pisa in 85 and a PhD from the Technical University of Delft in 99. Then from 86 to 88, he was working for ESA, for the European Space Agency, in Darmstadt, in Germany, and in the 88, he moved to ESA Research Technology Center, ESTEC in Norway, in the Netherlands. And since 2005, he is the head of Radio Frequency Systems, Payload, and Technology Division. So whenever you want, the floor is yours, and thank you very much.
Thank you, Anna, and good afternoon. Thanks for staying also this afternoon. I'm trying to talk about something that probably looks a bit different from the topics you have been hearing these days, but I will try to show that maybe it's not so uncorrelated, in particular for the evolution of 4th and 5th generation. So so my talk that is co-authored by one colleague and one an external person in a company externally working also for us. It's about the random access for satellite networks. I will try to show that there was quite some evolution in the last few years, and this evolution may be interesting also for the mobile wireless application. So probably you are not so familiar about satellites, so I will try to show you what are the trends. And also satellite is trying to cover as terrestrial applications, consumer broadband, but also machine-to-machine, and safety applications. You will see some examples, but just to give you an idea, air traffic management is a kind of application where satellite will play quite an important role. And recent events have been showing that the lack of this coverage by satellite can create some issue, like you don't understand where a plane is disappearing. So random access, you are probably familiar with, is very interesting because it's very efficient when you want to transmit isolated packets, small packets. And it allows to have a scalability, low delay, and typically is associated with a simple transmitter implementation. In satellite networks, typically random access is associated with some demand assignment. So you use random access as an initial login system. So when you enter the first time in a network, you use random access, but then you tend to use allocation of resources because random access is not good enough to support real traffic. What we have been considering a few years ago was the possibility to extend the utilization of random access to also support real traffic or signaling, and in general for all this kind of application like machine-to-machine, where you cannot afford to have allocation of resources upon the request to transmit a small packet. So here you see some example of what I mentioned of random access for SCADA or machine-to-machine, but also interactive broadband systems. Now, as I mentioned, I mean, today the random access utilization is very limited, but what we are doing in real satellite networks sometimes is to give some allocation of resources, and it's called combined free demand assignment multiple access, so that each terminal is getting some resource, and having some resources, if you have to transmit a small amount of data, you don't have to make all the process of requesting capacity and getting capacity given to you. This type of approach is not very efficient when you want to scale your network and when the number when the type of traffic, the number of users is very large and you are far away from Poisson type of traffic. In the meantime, it's okay. So in this case, you see what happens you have this CF DAM approach, and this is the load of the system, and this is the throughput. So for small loads, this approach seems to work quite well, and then you end off to a more demand assignment type of resource allocation. But when you apply traffic that is more realistic, more typical of internet, you can see that the throughput is very bad. So this approach is not scalable, is not very matching the needs of internet type of traffic. So now I will, by the way, I don't like to make outlines, so you will discover what I'm talking about, because I find outline in the presentation a bit boring. So you will discover the presentation while I'm talking. Now I'm going to talk about what are the, which probably you know better than me, the random access techniques in terrestrial, and what are the limits of applying these techniques to the satellite networks. So here you see some face that probably is well known to you, is Professor Abramson. That was the one that was inventing and implementing the Aloha network in the Hawaii island. So Aloha was one of the, it's very famous random access scheme, and there were variations on the theme of the Aloha that was slotted Aloha and diversity slotted Aloha, and more lately the spread spectrum Aloha. You will see what these random access techniques are capable of. But for what concerns terrestrial networks, there is a vast amount of random access techniques that are based on sensing the channel, because in terrestrial you can get immediate reaction about the possible existence of other packets that are transmitting on the same media. This is not the case in satellite. In satellite, typically we are using orbits that are creating delays in the order of hundreds of milliseconds. So you cannot sense the channel, it's too late. When you sense it, it's too late. So you can forget of applying all these kind of techniques that have been widely used in terrestrial. So that's why we have been first analyzing the limits of the techniques that do not require sensing, and then we have been looking at improvements that we believe may be useful also for terrestrial application. Let's start with the well-known slotted Aloha scheme. And one problem in general I found in random access, when you talk about random access, people tend to put the focus, the attention on the peak throughput. Because, it's known that you have a 0.36, the throughput, so you get this kind of throughput with slotted Aloha. In reality, for satellite for sure, but I think also in many other applications, you never operate close to this point. But when you look at the more interesting, when you look to the packet loss ratio versus the normalized load. So here is the normalized load, and here's the packet loss ratio. Here's for slotted Aloha. In satellite systems, we are targeting to avoid the retransmission of packets, so we operate at packet loss ratio below 10 to the minus 3, typically. So we are down here, well down here, so below 10 to minus 2, 10 to minus 3. You see that in this operating point, which is a practical one, the throughput is very bad. So we are talking about throughput of 10 to the minus 3 of 10 to the minus 3 in bits per symbol, which is pretty poor. So the 36 is not really interesting. Then you see also some the impact of power unbalance. There is some. These are simulations done with coding, and modulation is QPSK with some turbo codes. And then you see that if you have some power imbalance, here we are assuming some log normal distribution of the packets, you get a bit higher throughput. But still, in this region, performance are pretty bad. Then there was a scheme that is less known, but it was published quite some time ago, that is called diversity slotted Aloha. So the idea in diversity slotted Aloha is counterintuitive. So you, instead of transmitting in a frame a packet in a random slot selected randomly, you transmit two replicas of the same frame you want to transmit in two randomly selected slots of the frame. So you get more traffic in the channel, and you expect that performance are worse. In fact, performance are worse when you look in the conventional way. If you look at the peak throughput, yes, the performance is worse. But as we are interested in this region, performance are better. And they're better by, by this simple trick, you already get an improvement 15 times, capacity improvement compared to the slotted alloy. So it's already a good move because you are getting quite some improvement, but still the performance is not very exciting. Now, if you move to spread spectrum alloy, in this case also there is some coding on top. So you are transmitting, in this case you transmit, there is no frame, it's totally asynchronous. You transmit bars of coded bits, and then you let them collide, but you can recover most of the collision because you are using spreading. And by using simple, state-of-the-art, a few years ago, turbo codes, you get this type of performance. So again, it's better the throughput, but look more into this type of plots. If you look at the 10 to minus 3, that's not very readable. Anyway, we are here. We are in the range of 0.40, 0.5 bit per symbols. So we are much better, order of magnitude better than slotted alloy. But there is a but. As soon as you have some power imbalance that is typical, I think, in any practical system, terrestrial satellite, the throughput is dramatically impacted. It's so-called near-far effect. And then it's not good anymore. So you are losing a lot. So this is about the terrestrial, review terrestrial techniques. A lot of solutions have been studied that requires sensing the channel, not applicable to the satellite. Open loop solutions are available, but the performance are quite bad for the number of reasons, either because of the slotted alloy system poor throughput or the sensitivity to the power imbalance. So what can we do in satellite and maybe also for terrestrial? The first step into improving the random access performance was an evolution of this diversity slotted alloy. So we start from the diversity slotted alloy. So we have a frame, we have a number of slots. In the slots we are placing in random locations, say initially assume 2 replicas of the same packet. So far is like diversity slotted alloy. Then instead of doing the diversity slotted alloy that is basically just transmitting 2 replicas, hoping that one of the 2 will be received correctly in case of collision, here we do a further trick. We put in each packet some signaling bits that is telling to the demodulator where the replica is. So suppose that you transmit this packet and this replica. In each of these 2 packets, there will be information where you can find the replica, so that if you decode one, you can also try to remove, and you start to think about using interference cancellation, you can also remove the replica. So a few bits more in the transmitter, a bit more of processing on the receive side, because now you have to do, you have to store the frame, you have to look into the packets, and in case you detect the packet, you have to also try to eliminate the replicas. So in the demodulator that is now becoming a kind of frame-based memory, frame memory-based demodulator, you start to scan into the memory, and you look for decodable packets. In this simple case we are assuming here that 2 packets are colliding, we assume that you cannot decode. So the demodulator will go through, here nothing to decode. Then finally you get 1 packet that is without collision, so you can demodulate, and it was quick, but it was also canceling the replica packet in the other slot. And then you go on. Again, a packet that is alone can be decoded, and then you decode and you remove the replica. Now, instead of stopping here, you go back. So it's a memory, so you can go back, iterate. So you go to the beginning. Here, this guy is alone, and then you can decode and you can remove. So in this case, it is a simple example. In 2 iterations, you decode all the packets, even if collisions are present. What does it mean? It means that basically you're starting from a situation where there is quite a cloud of, if you look in the baseband domain, the signal is affected by co-channel interference and you cannot decode. But because of the iterative process, you end up, in this situation where you can decode, this is the same slot, but at the end of the iteration, you can recognize the signal that is removed because you have been removing the colliding packets. In terms of implementation, it's adding, okay, it's probably not very readable, but basically on the modulator, you just have to add simple things because you have to replicate the packet and to add some extra signaling. The signaling is coded together with the packet, so it's protected as the payload. Complexity is getting a bit larger on the demodulator side, but the demodulator is a kind of base station or gateway or whatever, so it's a central unit, so you are not so much affected by complexity issue. And what you have to add this memory-based processing, so you have to store the full frame and be able to iterate on this frame. When you detect a packet, normally you just get it out and that's it. Here you have to re-encode, remodulate, and you have to make a channel estimation, more accurate channel estimation for the useful and the replica packet. And then you have to cancel from memory. So all this, anyway, it's not a big deal of complexity. And you will see that it's fully implementable and it's not an issue. But there is a but. I mean, this is the kind of results we were getting the first time we have been working on this approach. As you can see, the green is this called contention resolution diversity slotted law because we are resolving the contention. Of course, I mean, again, if you look at the throughput, wow, it's better. Yes, it's better. But if you look at in this region that is for interest to us, the gain is there, but it's not dramatic. I mean, we are talking about 50 times better throughput compared to slotted law, which is not peanuts. But compared to diversity slotted law, it's not so good. Because the slope, it's quite bad. We didn't understand why at the beginning. And we thought that, okay, that's it. Then we also realized there was a bug in our simulator, because when we tried to increase the number of replicas, we were getting worse results. That was quite intuitive. You say, okay, you're putting more traffic on the channel. It's normal that you don't get higher throughput. Removing the bug, we found this kind of results after a while, also because people say, no, we don't buy. I mean, for this improvement, we don't buy the complexity. So this is the conventional slotted law. This is the initial diversity slotted law with contention resolution diversity slotted law with 2 replicas. And then we start to increase the replica. You see that the red is 3, and then this is 4 and 5. You see that there is this change of the slope that is very good, because it means that we are pushing the throughput. Again, this is normalized throughput. At 10 to minus 3, we are pushing toward 0.5, 0.6 bit per symbol. So we are talking about, in this case, we are talking about 600 times better than slotted law. Start to be interesting. So far it was there was some simplified analysis. We also found that as the normal slotted law, being the demodulator using successive interference cancellation is benefiting from power unbalance. So you see that the throughput is improving with power unbalance, so this is good, it's robust. So that's good news. But still, okay, all this was semi-experimental type of results. So it took us a while to get this kind of more analytical prediction of performance. Here you see that, I mean, there are dashed line, continuous line, and then dots and diamonds and squares and so on. So lines are theoretical results, prediction, and the others are simulation results. So you see that finally, took a while, we got a good understanding of this random access scheme. In this case, we can take into account an arbitrary number of replicas, arbitrary type of forward error correction scheme. We can use any distribution of traffic, so it's quite generic. This has been published recently, and I don't want to bother you with the details. It's quite boring stuff, but it allows to predict pretty well the performance. There are still some, it's not perfect because our theoretical approach is assuming that you have infinite number of slots per frame, which is not the case here. This issue that you say, okay, but there is a floor, I mean, it looks like the floor of turbo codes. No, there's nothing else, nothing to do with that. This floor is just because we assume log normal packet power distribution, and the tails of the distribution, I mean, it's just in AWGN at a certain point you go below threshold. So this is just due to the log normal distribution. In this case, we have 3 dB sigma standard deviation, but can also be predicted very well analytically, so nothing mysterious. And one of the points that I tried to show at the beginning was we had a problem with 2 replicas, which at the beginning we didn't understand. We thought it was inherent of the scheme. Instead, this problem is called loop phenomenon, and it was called also in this way by independent researcher in DLR. And it happens when you have this situation that when you have replicas that are exactly located at the same location. This is a simple case of loop, so that even if, I mean, it doesn't help you because you are stuck. If you are stuck, you are in a deadlock situation and you don't get out of it. The probability of having these loops, it depends on the number of replicas. And you see that this is for 2 replicas, the probability of loop versus the load on the MAC channel. And you see that increasing the replicas, the probability is going down. So using some analytical formulation, we can explain this change of slope, this kind of floor that due to the loop. And this was another element in understanding the random access scheme. Okay, so far, some simulation results, some theoretical results was looking good, but does it work? Yes, it works. It has been implemented. Okay, this was a prototype, so don't expect the ultimate integration, but all what I say was done, so with real channel estimation. So this is a satellite gateway demodulator. And these are the kind of, you will see later about standards. It entered also in the satellite standard. Here you see the comparison between the expected results from simulation and the ones obtained by measurements. And you see that the implementation loss is pretty small. So we have confirmation that this scheme is working. As you can see, I mean, we are in the range of 600 times better than slotted ALOA. It means that you can achieve, in a random access way, throughput that if you have 1 megahertz, assuming roll-off 0, you can get 600, 700 kilobit of net throughput in this band, which makes it already quite attractive because you don't have to allocate resources. So you will see that delay may also be positively impacted, and it's very scalable, or pretty well. So this was the initial idea, but the idea found some followers, and today there is quite some literature on this topic, because, as I said, the application, apart of the satellite that was maybe triggering the initial tackling the problem, is also now finding followers in other application domains. And the first kind of derived scheme is called irregular repetition slotted ALOA. The idea here, the intuition was, instead of having a fixed number of replicas, to have a number of replicas that is randomized according to a certain mass distribution. And this mass distribution was optimized, that's interesting, using the graph approach that I'm not familiar with, but they found that they can use the same type of analysis used for forward error correction scheme to optimize also the random access. And this was quite an interesting approach. Although this approach is nice, is very, I think, clean on the analytical point of view, but it's not accurate. When you try to predict the packet loss ratio with this approach, you don't get good results. You have to do more dirty type of analysis, but okay. And a kind of evolution of this scheme was, instead of having replicas, to have the redundancy, so you are coding the bits you want to transmit through the channel, and instead of repeating, you can spread the redundancy in different slots of the random access channel. So this is called multi-slots coded ALOA. And then there is another variation on the team that is coded slotted ALOA, combining the IRSA and the MUSCA. And then you get, so you combine the two. There is recently also some work done on network coding. It's called the Network Coded Diversity Protocol that is trying to apply this kind of techniques using network coding solutions. And finally, work is being published not long time ago for RFID interframe cancellation. So also for this kind of short communication devices, this kind of iterative cancellation of packets, but in this case through different interframes, so not inside the frame, infra-frame, but interframe. Here you can, I think the presentation will be available, you can find some reference. So far was a slotted solution, that has the evolution of slotted solution for random access in satellite. You saw at the beginning when reviewing terrestrial network solution that random access like spread spectrum ALOA is quite an interesting solution. So why you want to move out of a slotted scheme? For a number of reasons. You have to keep the terminal synchronized, and normally you don't like to keep synchronization because it's signaling. If you have a small network, maybe it's not a big issue. If you have a large network, you have problem of scalability. The other issue that I will present later is the aggregation of traffic. I mean, the traffic is supposed to be bursty. So when you aggregate few users, the burstiness is still visible. More users you aggregate, and less the burstiness is visible. That's an advantage of spread ALOA, because you aggregate more users, so you will see there is less fluctuation of interference. Finally, last but not least, this morning was a presentation on the energy efficiency, and also when you have power limitations. When you have a slotted system, you have to size the power you transmitted to aggregate rate of the channel. Instead, when you go to spread spectrum solution, you can size the power to the single user type of rate. So there's a big advantage in terms of power requirements with this respect. That's why we don't like the slotted ALOA. So instead, we like the spread ALOA. I don't know what I found these spread ALOA rings that I don't know what it is, but I found was nice. It's nothing to do with. I think it's nothing to do with this. Anyway, I was mentioning the story of the aggregation of traffic. In this plot, we try to show the distribution, probability density function of the traffic on a random access channel as a function of this. This factor, but basically it's a kind of normalized average traffic, this key over lambda. What happens is when you have a non-spread spectrum system, normally you are having distributions like this one, the green, the red, this kind of thing. You see that the amount of interference you see at a given time is changing in a quite extensive range. Instead, when you use spread spectrum, you aggregate more and more users, so the variation of the interference with respect to average value is getting lower and lower. Then you get this kind of distribution. When you have this large distribution, your system has to be designed to cope with the peak of the interference, these kind of peaks. And that's more challenging, so you have to keep your average load lower. More you aggregate and closer you can operate to the average interference to the peak level of interference. And that's one advantage of spread spectrum. Now, you find tons of papers on interference cancellation, but typically they are assuming continuous transmission. A lot are synchronous, all kind of things. There is much less literature related to multi-user, in particular successive interference cancellation for packet type of spread spectrum. And then we say, okay, let's try to reuse the experience we had on the slotted ALOA with contention resolution. So this idea to put the samples coming to a memory and then start to work on this memory, iterating. So what we are doing is exactly the same. You go to baseband, you put all the complex sample in the memory, and then you start to look for packets that you can decode. When we are in spread ALOA, differently from the non-spread system, we are talking about thousands of packets that are simultaneously present. So when you look, it's mess because it's a lot of signal, one on top of the other, spread spectrum signal. but you put a preamble that you know, and then some packet will be identified. Once you identify the packet and you decode, you cancel from memory, and you continue to search for packets in the memory. When you finish your memory that typically has a length that is, say, 3 times the burst duration, you go back. And this iterative approach is helping because you start to remove some packets, and the packets are affecting also the past. So when you go back, some packets that were not decodable will become decodable. And this is a bit the principle of this enhanced spread spectrum ALOA demodulator. So this is the window where I store the signals that is coming. I don't know what is inside, but I know that I'm looking to a certain preamble that is known. And then I start to scan the memory. And here you see the height is related to the power. So in this case, it's a bit simplified. The most powerful packet can be decoded and can be removed from memory. So I'm continuing my scanning. This packet is partially overlapped. In general, there are much more overlaps, but just to simplify. But being low power is not decodable until you see this packet can be decoded because it's powerful enough. And then you start to clean this one. And then you go back, and now this is powerful enough so that you can decode, and so on and so forth. And then you get all the packets decoded. Reality is not easy to visualize because there are so many packets that it's difficult to understand. But the system is igniting when the probability loss, packet loss ratio is as high as 0.5, 0.7. So situations which are typically considered unrecoverable are good because if you have 10,000 packets and 90% probability of loss of the packet, if you have, say, 1,000, then you have still 100 packets can be decoded. Once you have been removing the packets that typically are also the strongest one, and you go back, you will have other packets that can be decoded. So there is a kind of effect that is making the system working pretty well. Okay, in this case, I try to show that we had some understanding what we are doing, just to give you some. It's not too difficult. In this case, it takes a bit of patience to find something handleable, which can be handled. The point is that let's look at the performance of this scheme. Again, I like more the packet loss ratio because I see the real performance. You see that in this case, with power unbalance, because power unbalance is helping the successive interference cancellation, we can go in excess of 1.5 bits per chip. So if you have 1 megahertz, it means that you can transmit 1.5 mega chip in pure random access, totally asynchronous, with no power control. On the contrary, a bit of power unbalance helps. So it's not bad. We are now 3 orders of magnitudes, more than 3 orders of magnitudes better than slotted ALOA in a pure asynchronous mode. And we resolve also the problem that we had before, that spread spectrum ALOA was quite sensitive to power unbalance. In this case, because we have this iterative successful interference cancellation that is nothing fancy, but it helps, and it allows to operate with power unbalance and to get even better performance. So talking about power, we realized that power distribution for the incoming packets at the modulator was very important in this case. And there is an important paper from Viterbi that was showing that when you have SIC, the best you can do is to have exponential power distribution. Okay, he was looking at the case of continuous transmission, synchronous, but he was showing when you put your ultimate coding, distribute the power according to exponential law, which means in dB, try to have a uniform in dB power distribution. His analysis was formation theory type of analysis, so he was looking at assuming that there is coordination, the users are transmitting and they know what the others are transmitting. In this case, you have a large net, say millions of terminals, they don't communicate. And we found that through some analysis that this approach of this intuition of Viterbi is largely applicable also to this case. but you don't need to know what the others are transmitting. You have so many that you can just randomly generate the power according to uniform in dB distribution, and you get very close to the optimum. Now they are so close that it doesn't make sense to even discuss. When the spreading factor is reducing, the distance is growing a bit, but we are talking about peanuts. So the message is that we have a practical way to not only take advantage of the power imbalance that is inherent in the system, but you can also artificially enhance the power imbalance to get the best out of it, of this random access scheme. And these are some results. Sorry. There is some capacity bounds, and these crosses are experimental results. In fact, we have, I think these are simulation, but we have also measured the results very much in line. So what you see is that, okay, this is the capacity, the ultimate capacity. The green is the CDMA capacity with SIC and the coding rate 1/3 that we are using coding rate 1/3. And this is the random CDMA capacity. So we are, and this is some analytical prediction we have with this optimum. So here is the EB over N0 system. That is the average EB over N0 by all user population. And of course, there is a range, and the minimum and the maximum can be analytically or semi-analytically computed. The interesting point is that by increasing the randomness of the packets, you can grow the capacity. You see that we are getting 4 bits per chip. So if you have power enough and you can afford this randomization of power, you can get, I mean, numbers which are quite interesting. The modulation format we are using is BPSK. Okay, so it's turbo-coded BPSK, and these are quite small packets. So it shows that this power randomization is buying you a lot. And here you see also what happens if you limit your, in this case, the power was optimized. Here you're putting a limit on the maximum EB over N0. So, and so this is the EB over N0 maximum, and this is the range you are randomizing the power. You see that if you don't, I mean, you don't randomize, so it's fixed, all packets coming with the same power. This is a kind of asymptotic capacity. This is simulated. If you start to enlarge the randomization, you get more and more this kind of linear trend, so that you can increase capacity when you increase the maximum power of your incoming packet. And practically, I mean, this is quite an achievable point. I mean, this 2 bits per chip. So, again, this was some simulation, theoretical analysis, but now, does it work? Yes, it has been implemented a few years ago, and it has been tested. You will see some results. This, the first implementation was done, was funded by a satellite operator, and was done using a GPU-CPU platform, so software-defined radio, showing that, okay, it's quite complex, but can be done on a kind of PC with this GPU and CPU. It can process, in this case, was able to process 5 megahertz. So 5 megahertz software-defined radio implementation available, and it's kind of off the shelf nowadays. Here are results, maybe are not the latest results. They're showing comparison between the analytical simulation results and the measured results. I think here the channel estimation was still fine-tuned, but there was like a 10-15% loss between the ideal processing and the real processing. But this was measured, it has been tested over satellite, and is now entering into commercial product that is being developed by satellite operator. So it was quickly getting to the commercial application. Now we are looking into some evolution of this scheme, because what we have been using was a simple, relatively simple SIC, and you probably know better than me that if you want to get the ultimate capacity, you have to put an MMSE in front of the SIC. So a linear filter in front of the SIC, when you have the correct power distribution, gets you the ultimate. You saw there was a certain distance from the capacity bounds, although not too bad. So now we are looking into a way to practically implement this MMSE-seq with spread spectrum random access. And the approach that is being followed at the moment we are at simulation level is to use a multi-stage detector. So you, instead of doing a matrix inversion that is quite bulky because we are talking about quite large matrix, use this multi-stage approach that was published a few years ago. And it has the advantage that first the operations are kind of more conventional spreading and respreading type of operation, plus some multiplication. The coefficients can be computed offline, so they have not to be done online. And what you get is this kind of improvement. So if everything is done properly, so at simulation level, with ideal channel estimation, we can basically double the throughput of the enhanced spread spectrum ALOA. We call it MESE because it's MMSE enhanced spread ALOA. In practice, we see that this multi-stage detector is not trivial to be implemented. There are certain tricks, so you lose a bit with respect to this ideal channel estimation, but still there is a gain in the range of 50 to 80% if you want to push to the limits of the system. And finally, just to make it a bit more complicated, we want to go to non-slotted, non-spread spectrum random access. Why that? So you destroy all what we have been building so far, because there are a lot of legacy systems that are using somewhat slotted in frequency and or time. And these systems, like if you take 4G and maybe most likely also in 5G, they're going to have frequency division multiplexing and some slotted structure. So you don't want to, if you want to do a very efficient random access, you don't maybe want to deviate too much from this physical layer. So what you can do is try to find a solution that is easier to plug into an existing or being defined standard that does not include spread spectrum. And the other point is that getting rid of the synchronization, we believe is very good, because if you want to scale up the network, I think it's better to avoid that the terminals have to be kept synchronized. So the solution is a mix of the two previous solutions. If you take the idea of the contention resolution diversity slotted ALOA was to have replicas with information about the location of the replicas in each packet transmitted. But the problem was that you need synchronization, so you have to have a common time reference. All the terminals have to be synchronized to the frame that is a unique frame time reference in the system. And if you are offset, you have to adjust your timing to be with your slots aligned with the gateway or base station slots. So you need, in this system, you need the notion of frame and the notion of slots. But not necessarily, if you think about the spread spectrum type of processing that is a random access type of things, we take a window that is a bit wider, and we don't care about keeping the synchronization of the incoming packets. And that's the idea, what we called asynchronous contention resolution diversity ALOA. So the idea is that each user in its local reference is creating and transmitting packets in slots in a frame structure. So the frame structure is known. It's the same for everybody. And so the duration of the frame, the duration of the slot, the number of slots per frame is something known to everybody. But they are not synchronized. I mean, everybody has its own time reference and is shooting packets in this local reference, not taking care of the overall network synchronization. So what you have to do is that at the gateway, you have to widen your demodulator memory to encompass, say, 3 frames instead of 1. And then you have to operate in a way that is a mix between spread spectrum and contention resolution. So the space that you see in dashed line is the memory of the demodulator. And now you receive, it's a simplified approach, but I mean, you start to receive packets with replicas, use the same color for So the color is the type of terminal that is transmitting. You see the replicas have the same color because they contain the same payload information, but they are asynchronous. And the importance that you have a window large enough to include at least, say, 2 or 3, possibly 3 frames. And then you do a similar type of processing that we saw before. So you start to search because the preamble is known. And then when there is a collision, you are not able to detect. But then suddenly, here there is clean packet. So you detect the clean packet, you remove the twin packet, and you go on. Power is not the same. So this guy, you get it. And then iterate. Go back into memory, iterate. And little by little, you clean up all your you decode all your packets, you clean up your memory, and you are happy because now you are getting, on paper, good performance. You don't need synchronization. You don't need spreading. And it looks a good compromise when you want to avoid the spreading for philosophical, religious, or legacy reasons. Which is real. I mean, there's people that don't want to listen about that. I mean, in this case, I think perspective is a good solution. But if you don't want, you can get rid of it. So the demodulator is quite similar to the contention resolution diversity slotted ALOA, so I'm not going to repeat. There are some changes because the memory is a bit wider, but there is also some positive advantage. What we saw, the results are pretty recent, is that in this case, you get the best performance with only 2 replicas, not 3 or 4, like in contention resolution diversity slotted ALOA. This is the simulated performance analytical prediction for 2 replicas in asynchronous mode, and this is with the slotted approach. So basically, we get the same performance in terms of throughput and packet loss ratio as 3 replicas slotted with unslotted. 2 replicas means that you have less energy because you transmit for less time the same amount of power, and that's good. So you have less complexity in the demodulator because the complexity of the demodulator is somewhat related to the number of replicas you have to process. And there is also a big advantage in terms of latency. So this certain latency normalized to the frame length, and this is the percentile, the probability that you have this type of latency. And there is an advantage in the range, depending where you are, between 2 and 7, 2 and 8, if I'm correct. So it's quite a substantial reduction also in the latency of the system. So it looks quite promising. Some literature. This one is just appearing now on a publication, but you can find it. So now we have been looking at all possible permutations. Just quickly, some consideration on capacity, although I'm not the right person, but just to give you some feeling about this different scheme, in particular for the spread spectrum. So here you see the system loading is the number of active users normalized to the spreading factor, and this is the spectral efficiency you can get. You see that when you use only MMSE, you have a problem that there is an optimal system loading, after which you start to have a degradation in the capacity, whereas ideally you should continue to improve your capacity. So that's one of the limits. But when you use MMSE plus SIC, the performance is pretty good. In fact, is really on the capacity bound, and you see that you are better off than. It's not very readable. I'm sorry, it's not very. There's a problem with the. Anyway, this one is what you can get with MMSE SIC, and is better than other solutions. So, in particular, MMSE SIC helps when the power unbalance is limited. Then you get the best improvement in performance. And this is also true when you put the constraints on the modulation of, in this case, we have results for constrained modulation capacity. What happens is that when you use MMSE SIC, typically you have to use 2-dimensional modulation, namely QPSK, because you need more space for your MMSE filter. If you use just BPSK, you don't gain. And that's why iterative seek works best with BPSK, and MMSE seek works best with QPSK. Capacity is also confirming that, but also simulation results. So now from the information theory, we go to ground or to space, but I mean more practical system. So we had, going a bit in the history, I was reviewing that one of the early messaging system by satellite, in fact, was developed by ESA, and it was based on spread spectrum. Don't ask me why, because I was still studying at that time. But just to show that it was a random access system, it was spread spectrum. That was Anno Domini 1985. Shortly after, there was a first successful commercial system that was done by Qualcomm in the United States. This was used to link tracks to make reporting from tracks. I mean, you can see where the track is, you can see any telemetry from the track and so on. And this was also a system using kind of spread spectrum. It was using frequency hopping, but it was spreading as well. And the system is still operational and is, I think, is adopted in hundreds of thousands of tracks around the world. Then there was another commercial development that is called ArcLight by Viasat, and this case is using, so it's for, in particular for airplanes to transmit small packets, using spread spectrum with GMSK to have more constant envelope type of transmission. Moving closer to our days, there is a system for, it's called satellite triple play, because it's providing interactivity and broadband access to users not connected via terrestrial networks. In this case, there is some random access, but it's slotted ALOA, and it's more classical. So after small packets, they go through the slotted ALOA and then is getting capacity assigned. And more recently, and I think it will be also shown in the big fair that is next week or in 10 days in Amsterdam, is called Smart LNB, and it's kind of product that I was referring before by Eutelsat. So the idea is that instead of having a dish for television that is receive only, in the outdoor unit, in this box, there is also the random access transmitter, and in particular is the spread spectrum one you have seen. So you can imagine millions of users can get immediate feedback, which can be used for buying some program, also for the operator to understand what you're doing with your set-top box. And it can also be used for small internet access. Very cheap, because, I mean, we're talking about a very simple modulator, very low power. We're talking about milliwatt. That for satellite, I mean, having a transmitter, milliwatt is quite revolutionary, because normally we're talking about watts. And so the impact of these techniques, the contention resolution diversity slotted ALOA, has been included in the broadband satellite standard called DVB-RCS2, second generation. It's not compulsory, because the people that is making this kind of system, they still like DAMA. They are a bit scared, but it's there. There is another standard that has been published by ETSI that was for providing interactivity in mobile conditions, and the random access selected, it's also enhanced spread spectrum ALOA. And this was extensively tested, and was also the initial prototype I've been showing you before. So I'm skipping details. And then, as I said, there are also applications on aeronautical traffic management. There is a big program by the European Union to make airplanes connected via digital networks by year, that is shifting every year, but it was 2020, I think it will be 2025. Anyway, the idea there will be a terrestrial component and a satellite component. The satellite, of course, is able to cover also oceans and routes that are not covered by terrestrial networks. For the satellite component, the current baseline is to use enhanced spread spectrum ALOA, because it has been widely check against other random access techniques, and it was found to be the best option. Again, some readings. And finally, what else? But when we start to work in this one, we thought it was a matter of 6 months, and then we go to next topic. Somewhat we got stuck in this domain because there are so many things, interesting things, that we are still working on it. So, not presented today, but it's in the pipeline. We have now evolved some of the schemes, in particular the non-spread spectrum, to multi-frequency type of solution. In this way, we reduce the power, the peak power that the terminal needs, and we are getting performance that are very attractive. And I believe this kind of solution, multi-frequency, slotted or unslotted, it's potentially attractive also for the so-called terrestrial massive random access for 5G networks or variations thereof. As you have seen, we are researching now ways to get also better performance when the power imbalance is reduced, and this inclusion of MMSE on top of spectrum is very promising. We are also considering and studying the possibility to put continuous phase modulation instead of linear modulation to reduce the envelope fluctuations of more power and energy efficient solution. There is work ongoing with some university about optimization of the FEC scheme for random access. When you have this kind of iterative scheme, the optimal, and if you start to use soft decoding, the optimum FEC is still not completely clear. There are also papers proposing to do soft, what we are doing at the moment is still very basic. You can also think about do soft combining of the replicas and changing the way you distribute the redundancy across the replicas, and also interconnecting, say, base stations or gateways so that you can have a combined type of processing. And on top, there are all the issues above on the congestion control and so forth, which is not as critical as we think. So that concludes my talk. I think I'm on time. So.
Okay. Hello, my name is Thorsten Wild from Alcatel-Lucent. So thank you very much for this interesting talk, and I think I agree that those random access modifications and enhancements could serve indeed as a basis for inspiration for 5G systems. And maybe in 5G systems, the actual channel estimation might play a larger role. I don't know what your parameters are about in satellite communications, because when you think of 5G systems communicating with small packet services, the amount of training, so the number of pilot symbols is not that large. And your point was that the power imbalance is indeed a helper for SIG, but I see that the channel estimation errors will play against this a bit. So now it depends on the accuracy of your channel knowledge. So could you comment, please, on the length or the number of available pilot symbols you have in satellite systems, and what are your packet sizes? How many pilots do you have to estimate a channel, etc.?
Yeah, no, it's a good question because I didn't touch this point because I took out details, and one of it was the channel estimation. In fact, what we are doing is that in the decoding the packets, basically we use very much a standard demodulator. We don't do special extra pilots or longer preamble. But the trick is that once you have been decoding, you re-encode, so you remodulate, and then we do a refined channel estimation. So we correlate the samples in the memory with the regenerated packets, and then we are using the full packet for estimating the channel. And this is working pretty well, at least. We have been testing on fading channels, satellite fading channels, which are non-frequency selective. But also for phase noise is extremely important, because then you get a very accurate also phase estimation and amplitude estimation. And the same is for the replicas. We recorrelate where the replica is so that we don't make any extrapolation of phase, frequency, amplitude between the replica to the next replica. And this works pretty fine. We are getting cancellation in the order of in excess of 99% typical, but 99.5, I would say it's quite common, without adding extra complexity. The good point is the first time we have been implementing the CRDSA, that we are working with a company which was working on typically burst demodulator, and they use exactly the same channel estimation unit they were using in the commercial product. So there was no need for a part of the remodulation or re-encoding. So we have no experience with the terrestrial, but I'm quite confident it's not too bad. And so there is no extra overhead because of what we are doing.
Okay, thank you. That's good news. Can you give a number for your typical packet lengths you have in your communication?
Depends, but say most of the results I've been presenting here are 100 bits because it's easier to simulate. But we are in the order of a few thousand bits per packet. Okay. So it's pretty small.
Okay, thank you.
No, the MMSE.
Yeah, the MMSE.
And also MMSE SIC, after a certain point, there is a breakdown. Because the MMSE has started to have a problem of dimensionality. You have too many dimensions and you don't have space to operate your filter. So when the number of users relative to the spreading factor is start to be large, you run out of space. That's why you need two-dimensional signals, because at least you are doubling the number of dimensions, but then you run out of, so you have problems.
Any other comments? So, for thanking you. Yeah.
Thank you very much. Thank you.
Good afternoon and welcome everybody to the keynote speech of Riccardo De Gaudenzi. Okay? I am really happy that he accepted to come here. It was not trivial for him, I know, because he has a lot of work. Just as a short introduction, I'll tell you that he got his master's from the University of Pisa in 85 and the PhD from the Technical University of Delft in 99. Then, from 86 to 88, he was working for ESA, for the European Space Agency, in Darmstadt, in Germany. And in the 88, he moved to ESA Research Technology Center, ESTEC in Norwich, in the Netherlands. And since 2005, he is the head of Radio Frequency Systems, Payload, and Technology Division. So whenever you want, the floor is yours, and thank you very much.
Thank you, Anna, and good afternoon. Thanks for staying also this afternoon. I'm trying to talk about something that probably looks a bit different from the topics you have been hearing these days, but I will try to show that maybe it's not so uncorrelated, in particular for the evolution of 4th and 5th generation. So so my talk that is co-authored by one colleague and one an external person in a company externally working also for us. It's about the random access for satellite networks. I will try to show that there was quite some evolution in the last few years, and this evolution may be interesting also for the mobile and wireless application. So probably you are not so familiar about satellites, so I will try to show you what are the trends. And also satellite is trying to cover as terrestrial applications, consumer broadband, but also machine-to-machine, and safety applications. You will see some examples, but just to give you an idea, air traffic management is a kind of application where satellite will play quite an important role. And recent events have been showing that the lack of this coverage by satellite can create some issue, like you don't understand where a plane is disappearing. So random access, you're probably familiar with, is very interesting because it's very efficient when you want to transmit isolated packets, small packets. And it allows to have a scalability, low delay, and typically is associated with a simple transmitter implementation. In satellite networks, typically random access is associated with some demand assignment. So you use random access as an initial login system. So when you enter the first time in a network, you use random access. But then you tend to use allocation of resources because random access is not good enough to support real traffic. What we have been considering a few years ago was the possibility to extend the utilization of random access to also support real traffic or signaling. And in general, for all these kind of applications like machine-to-machine, where you cannot afford to have allocation of resources upon the request to transmit a small packet. So here you see some example of what I mentioned of random access for SCADA or machine-to-machine, but also interactive broadband systems. Now, as I mentioned, I mean, today the random access utilization is very limited, but what we are doing in real satellite networks sometimes is to give some allocation of resources, and it's called combined free demand assignment multiple access, so that each terminal is getting some scheme, and there were variations on the theme of the ALOA that was a slotted ALOA and diversity slotted ALOA, and more lately the spread spectrum ALOA. You will see what these random access techniques are capable of. But for what concerns terrestrial networks, there is a vast amount of random access techniques that are based on sensing the channel, because in terrestrial you can get immediate reaction about the possible existence of other packets that are transmitting on the same media. This is not the case in satellite. In satellite, typically we are using orbits that are creating delays in the order of hundreds of milliseconds. So you cannot sense the channel, it's too late. When you sense it, it's too late. So you can forget applying all these kind of techniques that have been widely used in terrestrial. So that's why we have been first analyzing the limits of the techniques that do not require sensing, and then we have been looking at improvements that we believe may be useful also for terrestrial application. Let's start with the well-known slotted ALOA scheme. And one problem in general I found in random access, when you talk about random access, people tend to put the focus, the attention on the peak throughput. Because, I mean, it's known that you have a 0.36, the throughput, so you get this kind of throughput with slotted ALOA. In reality, for satellite for sure, but I think also in many other applications, you never operate close to this point. But when you look at the more interesting, when you look to the packet loss ratio versus the normalized load. So here is the normalized load, and here's the packet loss ratio. Here's for slotted ALOA. In satellite systems, we are targeting to avoid the retransmission of packets, so we operate at packet loss ratios, and having some resources, if you have to transmit a small amount of data, you don't have to make all the process of requesting capacity and getting capacity given to you. This type of approach is not very efficient when you want to scale your network, and when the number when the type of traffic, the number of users is very large, and you are far away from Poisson type of traffic. The meantime, it's it's okay. So in this case, you see what happens. You have this CF-DAM approach, and this is the load of the system, and this is the throughput. So for small loads, this approach seems to work quite well, and then you end off to a more demand assignment type of resource allocation. But when you apply traffic that is more realistic, more typical of internet, you can see that the throughput is very bad. So this approach is not scalable, is not very matching the needs of internet type of traffic. So now I will, by the way, I don't like to make outlines, so you will discover what I'm talking about, because I find outline in the presentation a bit boring. So you will discover the presentation while I'm talking. Now I'm going to talk about what are the, which probably you know better than me, the random access techniques in terrestrial, and what are the limits of applying these techniques to the satellite networks. So here you see some face that probably is well known to you, is Professor Abramson. That was the one that was inventing and implementing the Aloha network in the Hawaii island. So Aloha was one of the, I mean, it's very famous, random access below 10 to the minus 3 typically. So we are down here, well down here. So below 10 to minus 2, 10 to minus 3. You see that in this operating point, which is a practical one, the throughput is very bad. So we are talking about throughput of 10 to the minus 3 of 10 to the minus 3 in bits per symbol, which is pretty poor. So the 36 is not really interesting. Then you see also some, the impact of power unbalance. I mean, there is some, these are simulations done with coding and modulation is QPSK with some turbo codes. And then you see that if you have some power unbalance, here we are assuming some log normal distribution of the packets, you get a bit higher throughput, but still in this region, performance are pretty bad. Then there was a scheme that is less known, but it was published quite some time ago, that is called diversity slotted Aloha. So the idea in diversity slotted Aloha is counterintuitive. So you, instead of transmitting in a frame a packet in a random slot selected randomly, you transmit two replicas of the same frame you want to transmit in the in two randomly selected slots of the frame. So you get more traffic in the channel, and you expect that performance are worse. In fact, performance are worse when you look in the conventional way. If you look at the peak throughput, yes, the performance is worse. But as we are interested in this region, performance are better. And they're better by, I mean, by this simple trick, you already get an improvement 15 times, capacity improvement compared to the slotted Aloha. So it's already a good move because you are getting quite some improvement, but still the performance is not very exciting. Now, if you move to spread spectrum Aloha, in this case also there is some coding on top. So you are transmitting, in this case you transmit, there is no frame,